Let's take a look at the stereospecificity here. Basically, what is the stereochemical outcome of this reaction? Thus far, I've been using primary substrates. They don't have any stereochemistry associated with them, and so there's nothing to observe that's special about the product. But let's look at this example here. Now I'm going to intentionally draw some stereochemistry on this molecule. Good question to begin with is, what is the stereochemical designation of this alkyl chloride? Think about that for a second, and then we'll work it out together. So if we look at this stereocenter here, which I'll put a red dot there, the highest priority substituent is the chloride, and then we have this long chain versus this shorter carbon chain. So the second priority substituent is the longer chain, third priority substituent is the shorter chain, and then if you want to, you could draw the hydrogen that is pointed backwards because the chlorine is on a wedge. And so we are ready to count 1, 2, 3 and observe the rotation of our counting, and it looks like we get counterclockwise, so I would label this stereocenter as S. And let's react this with I- and see what we get. And you know already how scientists could evaluate the stereochemistry of the product. We could use optical rotation if we wanted to. There are also some other spectroscopic techniques which are better discussed in second semester organic chemistry that we could use to establish whether this alkyl iodide was the R or the S version. Suffice it to say, scientists can investigate that, and they have determined that just about 100% of the time we get the inverted product. And so you can see instead of a wedge to my iodine, I have a dash. So the dashed chlorine was coming towards us. Now the iodine is pointed away from us into the screen. Let's establish the stereochemical designation of this iodine. Again, our stereocenter here, the iodine is the highest priority. The two carbon chains have not changed their priority, and so I can put them right there as well. I can count 1, 2, 3, and that looks like it's counterclockwise, but of course the hydrogen is now pointed towards us, so I need to reverse my assignment. So instead of counterclockwise, I would have clockwise. This is the R stereocenter, so you can see that we have undergone inversion. And let me redraw this molecule in a more suggestive manner, and I'm going to take the chlorine and draw it in the plane of the screen, and I'm going to take my other two carbons of my chain and also put that in the plane, and then I'm going to have a wedge and a dash here, and I think this is the correct way to redraw this molecule here. Well, let's make sure of that. Let's again identify the stereochemical designation here. The priorities haven't changed, so I can go ahead and number my substituents that way. I believe I forgot a carbon on this chain, so I'm going to add that. Let's go ahead and count 1, 2, 3 and see if I have drawn this correctly. 1, 2, 3 would get me a clockwise rotation. However, you see that the H is pointed towards us, so I need to reverse my assignment. This is still the S configuration. So I have redrawn this correctly. So this is always a check that you can use to make sure that you have redrawn a molecule correctly. And that's important because I want to show the inversion now. So let's go back to my reaction and get my iodine here. And a better way to show the arrows is this way. You can see that the nucleophilic attack on the back side, the side of the carbon away from the chlorine, helps to push off the chlorine. One argument for this method of attack, instead of coming in from maybe the front side, is that the chlorine is large. It has lone pairs around it that I have not drawn, but those lone pairs take up space. They are negatively charged. They probably would repel the negatively charged iodine. So the easiest way to attack is around from the backside. This carbon is partial positive because of the polar bond here, so that's attracting the iodine to it. The chlorine is partial negative. That's sort of a big ball of charge out in the front of the carbon, and that allows us to rationalize sort of the backside attack here. And so let me draw the resulting structure. I'm going to have the iodine on the the left side of my carbon now, the hydrogen is still on its wedge, the methyl still on the dash, but you see that I've sort of almost made an enantiomer, except that I and Cl are not identical. So let's confirm now that I still have, and I've now shown the R stereocenter. So the iodine is 1, the long carbon chain is 2, methyl is 3, hydrogen is 4. 1, 2, 3, that gets me a counterclockwise rotation, but of course the hydrogen is pointed towards me, so it should be clockwise. That means I've drawn the R stereocenter. And so you can see that this molecule up here and this molecule down here are identical. I've just used a different way of drawing to show how the backside attack of the iodine onto the stereocenter carbon allows for the inversion of configuration. And you can sort of see how the hydrogen and the methyl sort of sweep a little bit to the right. This propyl chain sweeps a little to the right. This is almost like an umbrella inverting in the wind. We've all seen that happen before. That's exactly how this process should be visualized in your head. Let's get some practice drawing the products of an Sn2 reaction. So here's an alkyl halide, alkyl chloride, SH minus. I don't always draw the lone pairs on the sulfur, but of course there are 3 of them, and we know that the mechanism involves these 2 arrows, nucleophilic attack and loss of leaving group. And since the sulfur is attacking from the backside, I need to show it on a dash in this case. And that's really it. That's all there is to the Sn2 mechanism. Here's another example. Both of these examples involve stereocenters. If it was a primary alkyl halide, we would not have a stereocenter, and it would be a little simpler to draw the product. Here again, OH minus attacking the backside of the carbon to iodine bond. This means the OH minus will be on a wedge now, and we've inverted the stereochemistry there as well. Substrate structure plays a role in this reaction, in affecting the rate of this reaction. So if we look at a methyl that bears a leaving group versus a ethyl that bears a leaving group versus an isopropyl versus a tertiary butyl structure, we can see that the rate is the fastest with the methyl, and it is the slowest with the tertiary butyl. And that's because of the steric hindrance at the central carbon. You can see how backside on a methyl carbon, there's not a lot of steric hindrance. And if you build a model with your model kits or come to my office and build a model, we can see this a little more clearly than on a screen. But the methyl has only 3 hydrogens surrounding it. Hydrogens are very small atoms. They don't take up a lot of space. And so this carbon is very open to backside attack. The primary carbon here, we can label that. The primary versus secondary versus tertiary, as you can see, we're getting more sterically hindered as we add more carbon groups around there. So instead of 3 carbons on the methyl, we have 3 carbon groups on the tertiary carbon. And that's going to severely hinder attack at the central carbon from the backside. It's very hindered. So basically, as far as an Sn2 process goes, the tertiary carbon is just about unreactive. So these are at the alpha position. The alpha position is the carbon bearing the leaving group. If we look at the beta position, which is that carbon, we also find a slight effect on the rate. If there's 1 substituent there at the beta position like I've drawn, not much of an effect. If there's 2 substituents, again, not much of an effect, because really we're talking about our nucleophile attacking this carbon, not the beta carbon. However, scientists have found that when there are 3 substituents at that beta position, then Sn2 chemistry rarely happens. So we'll say that this molecule is very unreactive towards Sn2 reactions. And this is called a neopentyl position. And that's because if we count carbons here, 1, 2, 3, 4, 5, this set of carbons, 4 carbons arranged around 1 carbon, is called a neopentane type molecule. And so this is a neopentyl position. This bromine will not be substituted via Sn2 because of the huge bulk next to the carbon bearing the leaving group. There's just no way for nucleophiles to get into this position. And it looks like that wouldn't really be a challenge according to my blue drawing right here. But if you make a model of this, you'll see how this group can effectively screen the alpha carbon in this case. Some other examples of neopentyl positions. We don't necessarily have to have a straight chain, but we could have this situation where this carbon also is quaternary. It has 4 carbons attached to it, including the alpha carbon, and thus this position here would be a similar type of neopentyl position. That bromine will not participate in Sn2 chemistry. Another example, maybe we have a longer chain with more substitution at that beta position. Here's the beta position again with a blue dot. The alpha carbon, again, indicated by the arrow. That's going to be an unreactive alkyl halide towards Sn2 chemistry because of the high steric hindrance at the beta position.